Hello, ladies and gentlemen. Good morning, and it's Dr. Jones again. Let's pick up our conversation from last week when we were talking about pH, acids, and bases. So, if you recall, if you're looking at the pH scale, we're only concerned with the hydrogen ion concentration. And here's what we're saying. The more hydrogen you have, the more acidic a solution is. The less hydrogen you have, the more basic. So that's all great, fine, and dandy, but what does that have to do with what happens out in nature or what happens out in the real world? So one of the things I want to talk to you about is how acids not only react with bases, but how they react with metals, because that's one of the things about an acid that gives it such unique properties. So here's what we have here. We have three different types of metal. This first metal is iron, and this is really what iron looks like. This one is magnesium. If you notice, magnesium has a completely different consistency, a completely different shape and properties than our iron. This is zinc. And a lot of people think about zinc, they think about, oh, aren't those supplements that I add into vitamins? Yes, there are zinc supplements. But this is what the metal actually looks like. And then the last one we have here is copper. So we have some copper beads. Now, one thing about acids, all acids are not created equally. Here's what I'm talking about. So, this is hydrochloric acid, okay? And one of the things that is unique about hydrochloric acid is that it is considered to be a strong acid. Here's what I mean. pH paper is a easy way of being able to figure out where an acid or base falls on this scale, okay? So if you're looking at this, most acids and bases are clear. So by looking at them just with your eyes, you can't tell exactly where they fall on the scale. However, if I take and dip the pH paper into an acid, I can quickly see where it is. And if you notice, wow, this is very acidic. So for hydrochloric acid, we're talking about something that has a pH of 1. pH of 1 is way down here. Very acidic, almost like gastric acid, okay? Now, this other acid that I have here is called acetic acid, all right? Acid's in the name, however, like I said, all acids aren't the same. So if we're looking at acetic acid, okay? Notice acetic acid has a pH somewhere around, somewhere between 4 and 5. So it is not as acidic as our hydrogen chloride. So think of it being somewhere here, like around orange juice or lemon juice, okay? And just to like round things off, this is sodium hydroxide. So by the name, you can already tell, wait a minute, something's a little different. Well, sodium hydroxide has different properties than both our acetic acid and our hydrochloric acid. And those properties tend to align with bases. This is like a 13-14. So if we're looking at 13-14, we're up here. We're like around soapy water or bleach. Okay? And so, again, one thing that's great about pH paper is it kind of tells you where your solution falls, but it also gives you an idea of how strong it is. So, let's look at our two acids and how they react with metals. So, first of all, I'm going to start with our weaker of the two, our acetic acid. So, think of this as orange juice, lemon juice. Okay? So, we're going to add it first to our again, this is our iron. Then we're going to add it to our magnesium, our zinc, and finally our copper. Okay? Going to work those around and see if we see any reactivity. Now, if you notice, you're getting bubbles with the magnesium. You're getting a few bubbles with the zinc, but there's like nothing happening with the copper or with the iron. We would call that a definite reaction. But with the other two metals, not so much. Okay? Now, let's try our hydrochloric acid. Violent reaction. So, notice, hydrochloric acid reacted very similar to the acetic acid. However, it was a more violent, a more robust reaction. And here's why. The big difference between our hydrochloric and our acetic acid was the amount of hydrogen ions. Basically, think of it this way. If I gave you $100 and said, go to the mall or go online, do your worst damage, you're not really going to be able to do a whole lot of damage. I mean, $100 can't get much. But if I gave you 10 grand and said, go crazy, you could do a lot of damage with $10,000. And no limits. That's the 10. This is the 100. Same thing. When you have a stronger acid, you can do more damage, which is why if you look at what gastric acid can do compared to like orange juice, this stuff breaks down food. Orange juice, burn your eyes, but not too much beyond that. Now, let's try something though. Let's look at our base. Here we go. Sodium hydroxide. What does sodium hydroxide do with metals? Well, does it do anything to our iron? Nope. Did it do anything to our magnesium? Nope. Did it do anything to our zinc? Nope. Did it do anything to our copper? No. Well, why not? Well, think about it. Yeah, it's a strong base, but it doesn't have very many hydrogen ions. So although, this is a very strong base, it's a weak acid. So it had no reactivity, whereas our acids did. So that's the main reason why when you're looking at a pH scale, you have to think about, well, what is it that is going to actually react with the metal or with the skin? Okay? Now, one more thing. How can you use a base to neutralize an acid? Well, let me show you. So here are three solutions. 1, hydrochloric acid. 2, acetic acid. 3, sodium hydroxide. This is another kind of indicator. It's called phenolphthalein. And what it does is, if you're in an acid, it doesn't really do a whole lot. In a base, turns pink. So basically, this will tell you when you've taken an acid and turned it into a base. So watch. And a couple more drops, So let's compare. Here is my sodium hydroxide. Let's add a drop of sodium hydroxide to our acetic acid. That's 1. Wow. Immediate reaction. Let's add it to our hydrochloric acid. Immediate reaction. But watch this. You spin this, becomes clear. You spin this, it also becomes clear. There's this thing called titration, which is like a balance. When you titrate, you basically add enough base to neutralize an acid. So let's do 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 drops. Let's see what happens. Goes back to being clear. 11, 12, 13, 14, 15, 16, 17, 18 drops. Yeah, I've watched too much of the count. 18 drops, nothing. 19, 20, 21, 22, 23, 23 drops. Ha, ha, ha. Now, notice. 23 drops. Oh, okay. We got something. Watch this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 30 drops. Spin it. Goes back to being clear. Basically, it's going to take more of this base to neutralize this acid than it would to neutralize this acid. So, case in point, if you have baking soda versus having soap in your eyes, you'll be able to flush the baking soda out easier than the soap. Why? Well, because it's closer to being neutral, being like water. Okay? Same thing. If I have tomato juice versus lemon juice, the tomato juice will be easier to neutralize than the lemon juice. Okay? So again, two things I want to bring home. First of all acids aren't the same. Some are more acidic than others. What makes an acid acidic? The amount of hydrogen ions. Bases, although they may be very, very strong, don't have as many hydrogens. So what may react with an acid won't react with a base. And more important, if I have an acid and I want to neutralize it, I can neutralize it with a base. But if the acid is strong, it's going to take more of a base to neutralize it. I hope this helps you guys with your understanding of why acids and bases are so important to us in science. Have a great day.